Shamini. Good seeing you. All right. I just want to make sure that you guys received the stuff, right? PowerPoint presentation is a PDF file. I also put one file called Properties of Hydrogen. It's a long file. So here is what we will be doing. As you all know, we have the final scheduled for December 14th. Is that correct? 14th is a Monday. So I'll keep the exam open for about 3 hours. So you can pick up any time between 11 to 2:30 and finish the exam. Do you guys have any conflict of exams during that time? Is there anyone who has a final scheduled around the same time on December 14th? Can you please check and let me know before it is too late? Hearing none, I would assume that you have no other conflict with the exam.
There is a message in the chat, Pastor.
Messages. Okay, let me see. So how can they schedule two exams like that? One from 12:30 to 2:30 when they have an exam at 11 o'clock, right? Can we make it maybe in the evening between 4 to 7? Is that okay to all of you?
Wait, so Professor, we'll be able to only take it from 4 to 7? Like that's the only time we can take it?
Right, 4 to 7 or 8, depending on how much time window that you want. But once you take the exam, you will have exactly 120 minutes to finish it.
Okay.
Is that okay?
I think I might have one from 5 to 7 on Monday. I can check, but
or if you want, I can have the exam on Sunday, if that is agreeable to all of you, because I'm sure there are no exams on Sunday, right?
Can we just open it so it's like available all day and then we take it when we don't have other finals?
You mean for Saturday and Sunday and Monday, both days?
Well, just opening Monday, like all day Monday.
Right, just like all day if it's open from like morning till evening, and then like we still have only 120 minutes to do it, but at least we like get it done when we have an hour and a half or so or 2 hours to do it.
All day Monday would be good.
Can we do it from Monday morning 8 to night 10?
That sounds good.
Okay, you can pick it up any time and then finish the exam, but after 10 o'clock in the night, you will not be able to start. So when you start the exam, you make sure that you have nothing else going on, because once you start that, right, you cannot come back to it. Is that agreeable to all of you? So I'm going to make it, right? So Monday, December 14th, from 8 a.m. to, I would say, 10 p.m. Is that good?
Yeah, that works.
That works? Excellent. Thank you. All right. So, Michael, is that all right to all of you who have been chatting with me on this?
Yeah, that works for me. Thank you.
Excellent. Excellent. All right. Okay. So here is what I plan to do. Today, we'll have a quick lecture on the medicinal inorganic chemistry. Part of the reason why I include this in this class is because some of you are biochem majors, and most of you may be thinking that pharmaceutical drugs are all organic. I'm just going to prove that wrong to you, because that's not how it goes. There are lots of drugs based on inorganic, and we're going to review some of them, if not all. And there are many drugs based on inorganic chemistry that have been approved by FDA for treatments, various diseases. Okay, so it's a very emerging field. This is how the humanity has started. The inorganic chemistry was the primary defense for the humanity against diseases. So it started about thousands of years ago. We're going to review that history too. And starting around 1950s to 60s, we have had a lot of organic drugs coming to the picture, both synthetic and natural. When I say synthetic, that means the drugs that are prepared in the lab. Natural means, heterocycles from the plant-based drugs that have been isolated and used as curative agents in the pharmaceutical industry. So despite all that, we still have a lot of inorganic components, so we're going to review that stuff in this lecture. Next Monday, we will have a lecture at 11 o'clock to talk about hydrogen. Is that okay? We'll quickly review some of the properties. We may not be able to complete the presentation. The reason I gave you the presentation is I want you to go over that and at least have an idea about how hydrogen is used today, just one element in the periodic table. So if you were to use the same template and use the remaining part of the periodic table, you can see that you can have entire 4-year course, just the bachelor's, doing inorganic chemistry. That's how extensive the inorganic chemistry is. So just to give you a flavor of that, we'll do something on hydrogen that day. And the following Wednesday, which I think is 9th, I believe. Is that correct? December 9th is Wednesday. Around the same time, we will do a final review. Like if you have any questions before you go for the exam on Monday. Is that agreeable to all of you?
That sounds good.
Sounds good? All right, thanks, Alexis. All right, so I'm going to do something that I have not done that in the past. So we will see if I can share the screen with you. So let me see if this allows me to do this. Let me see. Can you see the screen that I? Can you see my screen?
No, not yet.
Not yet. So I'll keep trying until we get to a point where we can see the slides. Let me see if there is a share screen. I'm trying to see if you can see my screen.
We can see it now.
Okay, what do you read on this? Do you see 2 panels or 1 panel?
We see 2.
2.
2 panels, okay. The left panel says medicinal and organic chemistry in my name, right? All right, so the next panel will come to the main panel. So this lecture is going to be the applications of inorganic chemistry, especially coordination complexes, simple salts, and how they're used in the medicinal industry. So today's outline is going to be a brief history of inorganic chemicals. I'm going to review almost 6,000 to 7,000 years of history of inorganic chemistry as therapeutics by humanity from all over the world. And the next thing is antacids. It's $1 billion industry based on inorganic chemistry. Most of the antacids that we consume, whether it is, the milk of magnesia or Tums or Alka-Seltzer or any of these things that we take, or the counter drugs for controlling the acid reflux, they're mostly inorganic in nature. And then we'll talk about metals as curative agents, as well as complexes as therapeutics. So in variety of diseases, right? And finally, we'll talk about modern concepts, including the diagnostics, how inorganic chemistry helps the medical community in terms of diagnosing diseases and so on and so forth. All right. So medicinal inorganic chemistry is practiced at least for 5,000 years. There's no question about that. The very first evidence that gold was recognized in Arabia, which is what we call the Middle East these days, and China for 3,500 years. So if you take the gold and put it on wounds, surprisingly, gold had that, wound curing ability, which was surprising to them. But again, please keep in mind that when we are looking at these years, thousands of years ago, there was no periodic table, there was no atomic structure, there was no, the Bohr's model, or none of these things existed. There was not even a periodic table in those days. So they kind of found accidentally that gold had this therapeutic value. After about 2,000 years, they found zinc also had beneficial effects in terms of healing the wounds. That was discovered by Egyptians. That was amazing discovery. Even today, zinc is one of those elements that is being pushed for curing COVID. I don't know if you have heard about the respiratory illnesses that are caused by COVID can be cured with zinc. And this is one thing some of the medical community is putting forward in terms of taking zinc tablets or zinc supplements. The antibacterial activity of gold salts were reported almost 1,200 years ago. Not the elemental gold, but the salts of the gold. So the very first tuberculosis medicine was a coordination complex that has potassium, gold, and 2 cyanides. How do you call this one? This is potassium dicyanoaurate 3, right? Aurate 1 complex, right? So this is what was discovered in 1912. Prior to this drug, there was no cure for tuberculosis. So when somebody contracts TB, that's almost like a death sentence for the people. So this is amazing. It saved the humanity from the pandemic of TB. In fact, the first Nobel Prize in medicine went to Paul Ehrlich, who reported the structure-activity relationships of arsenic-containing drugs towards the treatment of syphilis. Again, prior to the arsenic drugs, there was no cure for syphilis. Syphilis was almost like a death sentence on people. So if they contacted syphilis, there is no cure for this, they have to die out of this thing. So he also showed the toxic effects of lead in central nervous system. For these 2 discoveries, the first Nobel Prize in medicine went to a person who is an inorganic chemist. That is very comforting that inorganic chemistry has definitely a role in the pharmaceutical industry. Moving on, when you look at the human body, the constitution of the human body, you will find that majority of human body contains inorganic elements. Like, for example, if you take 70 grams, an average weight of a human being, the oxygen content in the body is almost 45.5 kilograms. And oxygen exists in a variety of forms, both molecular oxygen as well as the oxygen in the water and so on and so forth. Carbon is next in the line with 12.6 kilograms, hydrogen 7 kilograms, nitrogen almost 2 kilograms, calcium about 1 kilogram, phosphorus about 700 grams, and so on and so forth. As you go down to zinc, it's almost 2.3 grams. And there are other elements which we call the trace elements like bromine, fluorine, strontium, copper, aluminum, lead, antimony, cadmium, tin, iodine, molybdenum, and manganese. They all together contribute less than 2 grams. But the issue is as following. Even if there are trace elements, any deficiency or excess in the trace elements leads to, again, a disease state. So this is very important to maintain the balance of all these inorganic chemicals properly in the human body. For example, zinc. Without the zinc, the insulin will not be stable. In fact, zinc is responsible for the stabilization of a variety of proteins and peptides in the human body. Almost 30 different proteins and peptides are stabilized by zinc. As you all know, insulin is a peptide, right? But insulin will not be stable unless you have zinc in it. So as you can see, the inorganic chemistry plays a pivotal role in terms of controlling the biological activity of the peptides and the proteins, right? Similarly, copper deficiency can lead to issues, problems, or copper excess, which is what sometimes dogs have a problem because sometimes some of the dogs get copper excess. When that happens, again, there's a problem. Similarly, you have heavy metal contamination, mercury, lead, antimony. These are all toxic elements. If you accumulate that in the human body, as you can see, that those can cause a lot of problems too. So in a way, inorganic chemistry is intricately related to the human physiology. That's what we're trying to establish here. Now, just with any pharmaceutical drugs, there are at least 2 types of drugs. Drug type A, which are extremely harmful even in small amounts, or type B, where they have beneficial effects up to critical concentration, but if you exceed that concentration, they turn out to be deadly again. So that is true with all pharmaceutical drugs. They all work at certain dosages. If you decrease the dosage or increase the dosage, the beneficial effects are not seen in these molecules. Okay. All right. So why metallo drugs? Metals play a critical role in all living systems. Okay. It's known for many years. Iron, for example, is the cause of all the whales and the sharks, where they travel miles and miles for long distances and come back to their habitat without using a GPS. Isn't it amazing that they know exactly? They travel almost 3,000 miles without any map, without any navigational system. They go to certain parts and come back again 3,000 miles to the same place where they started. If you really think about this, it just kind of, it's crazy. How do these animals do this? Apparently, the iron plays a very significant role in terms of giving their navigational abilities. One of the reasons why metals play an important role is metals lose electrons to form cations. Therefore, inherently metals or metal ions or metal cations are electron deficient. However, on the other hand, if you look at the biological molecules like enzymes and DNA and peptides, these have electron-rich atoms like nitrogen, oxygen, elements that are electron-rich, which are basically Lewis bases, right? So what happens is there is always an interaction between the metal cations and the biological molecules, which you can call that more like, I would say, Lewis acid-base reaction, right? So the metal cations act like Lewis acids, and the biological molecules act like Lewis bases, and there is an acid-base interaction between them. And the affinity of metals for electrons is also responsible for functions that are crucial for life. For example, if you want to transport oxygen molecule in the body to the cells, right, various cells, that is delivered by hemoglobin. Hemoglobin is a complex containing iron. So this iron, which can exist both as 2+ and 3+, can bind with the oxygen and transport the oxygen to various cells in the human body. So without the iron, you will not be able to survive even. So for example, if somebody has a cyanide poisoning, what cyanide does is it kind of blocks the iron because it makes iron cyanocomplex. And once the iron is deactivated, it will not be able to transport oxygen that causes to death. So that is how serious this is. Zinc is a vital component of insulin, a substance vital for glucose metabolism. So without the zinc, insulin will not function in terms of controlling or managing the glucose content of the human blood. Now, metals owing to the Lewis acidity catalyze several organic transformations efficiently and selectively under physiological conditions. This is, again, a very important topic. If you really look at this sentence very carefully, you find that when you're doing organic synthesis in the labs, you are free to add HCl, H2SO4, or AlCl3, different things. You can create extremely low pH conditions, highly acidic conditions for carrying out organic reactions. But can you do that in the human body? Because our physiological pH is not acidic enough to transform a lot of organic reactions. We all know this. So how do we carry out these reactions? So what happens is when you have the metal ions, they create locally, not through the entire body, but locally they create an acidic environment that allows the biological transformations to happen. So this is how metals play a very important role in the biological systems. So then the question is, what is medicinal inorganic chemistry? Since nature made such an extensive use of metals in living systems, the idea is, can we retune the concentrations of the metals in a way that we can get a beneficial effect? So that is the purpose of studying medicinal inorganic chemistry. Can coordination chemistry, also known as organometallic chemistry, be used to design curative agents? We're going to give you a lot of examples as we move through the presentation. And the biological activity of many proteins and enzymes is attributed to the metal centers. So without the metal centers, the protein folding or the protein activity is completely compromised. So medicinal inorganic chemistry probes into the feasibility of using different metals and substrates for modifying the biological functions. So that is the objective of medicinal inorganic chemistry. Now, medical applications of inorganics are several. Primarily, they are used as drugs and diagnostics, like barium, for example, right? The contrast. And you also have radioactive isotopes that are that serve as curative drugs for cancer. And there are small molecule radiopharmaceuticals and diagnostic imaging that are done by gadolinium, for example. One of the rare earth elements is very important in terms of giving you extremely good pictures of the human organs to see where the damage is, where the cancer is. You can map it very nicely. Similarly, if you take X-ray, right? When you take the X-ray of lungs or broken fractures, we use extremely small amounts of small dosage of X-rays, but we have what we call X-ray phosphors that are coated on the film. So even a small amount of X-ray, when it passes through, it activates that phosphor and gives you an image. That's how the doctors figure out where the fracture is. So if you really look at that whole process, that's all inorganic chemistry there. So this is where inorganic chemistry comes in a variety of ways in terms of creating, pharmaceutical activity in the molecules. So metal blast X-ray contrasting media is again very commonly seen. I don't know how many of you have seen, maybe you or one of your relatives must have gone to hospital and you want to get an X-ray done and the doctors ask you to drink quite a lot of barium sulfate. It's not a pleasant compound to drink, but that kind of enhances the contrast of the species. So this is again inorganic elements. And metal complexes as photoradiosensitizers. So this is also emerging field which they are exploring now in the medical industry. So how do we classify the inorganic drugs? Basically, we classify the inorganic drugs as three types. One is active complexes. The entire complex acts like a curative agent. For example, platinum-2 complexes or ruthenium-2 complexes for cancer, and bismuth-3 complexes for gastrointestinal diseases, pepto-bismol, and so on and so forth. For the platinum, as you all know, cisplatin, which is dichlorodimine platinum-2 complex, is still used as a chemotherapeutic agent. And now people are looking at ruthenium complexes too as a way of getting rid of platinum and using different complexes for curing the cancer. That's one type of drugs. The entire complex acts like a drug molecule. There are other cases where an active element or the metal ion is important, but not the counter ion. For example, lithium ions are known for curative agents for manic depressive psychosis, or silver or mercury too as antibacterial agents, and gold is used in rheumatoid arthritis. In these cases, the metals are more important, not the counter ion. So for example, if lithium is used as a drug, the activity comes through lithium plus ion, but not the counter anion. It could be lithium chloride, lithium nitrate, lithium acetate, lithium phosphate, it doesn't matter. It's just the lithium that is important. That is one class of inorganic drugs. Finally, you have other class of inorganic drugs where the ligands are the drugs, not the metal. For example, nitroprusside, which has both NO and CN functional groups, and this complex releases the NO, nitric oxide, which acts like a hypotensive agent, that is a muscle relaxant. So if you want to relax the muscles, this is the complex in which iron is not important. Iron has no pharmacological activity. It is the ligand that gets released from the complex that is responsible for the curative properties.
Dr. Terry?
Yes.
So is there some kind of advantage for having the ligand in the metal complex rather than just the ligand as the drug?
That's a good question. See here, what happens is, are you a chem major or a biochem major?
Biochem.
Biochem. Are you taking advanced inorganic? No. Are you registering for advanced inorganic chemistry next semester?
No.
All right. Well, I'll tell you briefly, but there is an electronic reason for using this nitric oxide ligands. Because nitric oxide as a gas, it's very difficult to administer, right, into the body to a particular space. But if you take the complex, this complex slowly releases NO. It's not a burst of NO that goes on, extremely small concentrations. because this complex, iron 3 complex, is so labile. Labile means it can exchange the ligands with other incoming ligands. So that's how the NO is administered into the cells in a very slow, subtle way. Okay? Yeah, the activity comes through NO, but NO cannot be directly injected into the system. So we do it cleverly by using nitroprusside complexes. Would that make sense to you?
Yes, thank you.
Samantha. All right, good. Keep asking questions, no problem. All right, so the next one is, if you now look at the periodic table, this is the medicinal periodic table. In other words, it tells you how many elements are useful in the pharmaceutical industry. So in the symbols in the white front, like potassium, sodium, hydrogen, magnesium, calcium, those are all in the white front. Can you all see that in the presentation that I gave you? I don't know, but you can definitely, I think we're going to record this conversation too, so we'll upload this one once this is done. But in these elements, these are all elements that are essential for humans. Remember, we talked about several elements in the previous tables. Those are all in the periodic table. And when you have a green fill, like cesium, radium, actinium, half of yttrium or strontium, these are all used as medical radioisotopes. And elements that are currently used in therapy have a blue fill, like the platinum, gold, silver. These are all used currently in therapeutic applications. And the diagnostic ones are given in the orange fill, like barium, for example, or the rubidium, zirconium, indium, thallium. Have you heard of thallium stress test? Maybe not, right? If people have problems in the heart problems, right? The first thing they will do is EKG. And if the EKG is normal, but the patient still feels bad, then the next thing they will go for is ultrasound, 2D ultrasound, 2D echocardiogram, they call that. But even if that cannot resolve, then they ask the patient to go through a stress test in which they inject small amount of thallium, and that with a red dye, they kind of ask the person to do a treadmill for about 20-30 minutes, and then they look at the picture to see how well the blood is being circulated. Are there any blocks in the arteries? So those are all wonderful things that you can do. This is called thallium stress test. All right, so these are all used as diagnostic ones. And more importantly, the titanium and tantalum are used for implant applications. As you all know, if somebody has a broken bone or a plate that needs to be replaced, they use a metal, right, inside. They use metal screws, metal plates, and those are titanium or tantalum. You can't use iron or gold or platinum into that. For some reason, the body does not recognize titanium once it is inserted. So it does not trigger the immunoresponse that gets triggered when you have other metals. So titanium, recently I have seen reports that vanadium also is a little bit tested, but vanadium is more active compared to titanium. So titanium is still the most favored metal that they use to insert into the body, like plates or dental replacements. They have the screws that they use. All these are all made from titanium. So this is how the periodic table is useful in a variety of medical applications. Now, these are some of the inorganic-based drugs that have been approved or various stages of approval from the FDA. So bioplatin, which is a dicycloplatinum, is a platinum-based. Lipoplatin is again a platinum-based. It's in phase 3. Oxaliplatin, so instead of using amine groups, they can use oxalate groups. And that is for the colorectal cancer. It's a deadly disease. And it has been approved by FDA for the treatment. So this is a platinum-based drug. Similarly, there is Solasia Pharma has darinospirin, that is a T-cell lymphoma that is basically based on arsenic here, not platinum. And Trisoneox, that is again arsenic-based, that has been approved. So Patheon Incorporated has developed zinc complex Voriostat, that is for the cutaneous T-cell lymphoma, that has been approved. As you can see, it is the zinc that is the active pharmaceutical ingredient, API. Similarly, Mayo Clinic has used gold to recurrent ovarian cancer. It's in the pilot stage right now. So you can see there's several drugs, technetium-based, gallium-based, radium-based, lutetium-based, that is being at the phase 2 now, small cell lung cancers. So these are all what we call very deadly diseases where you don't have the organic drugs, but you go with inorganic counterparts to create new therapeutic things. They make a lot of money. The companies make a lot of money using different metals. So the next thing is, of course, antacids. That's a $2.5 billion industry every year in this country alone. So part of the reason is, as you all know, most of us don't take food at a regular time. How many of you have breakfast exactly at 7:30 in the morning? How many of you have lunch exactly at 1 o'clock?
I wish.
Uh-huh.
I wish.
I wish, I know. And I'm no exception. I'm not saying that I'm not, I sometimes have to adjust it. And similarly, if you have dinner, how many of you have dinner at 6 o'clock? Very rarely, we have time to do this. So, but what happens in human body is the human body prepares an acid in anticipation of the food. And if you don't take the food, that acid stays in the liver and starts giving you this acid reflux. So that is when you have antacids. Similarly, emotions too create acids. If you are really angry, if you are really happy, those human emotions also change the biochemistry. I don't know, if you are really angry with something, how many of you feel hungry at the same time? Hungry and angry at the same time? Very rarely do you get that, right? So human emotions play a very important role, and especially stress also contributes to the acidity. So we consume a lot of antacids, and most of these antacids, whether it is TUMS or alcohols, these are all basically based on inorganic carbonates or oxalates. So what are antacids? Basically, these are substances that neutralize stomach acidity. As you all know, most of the stomach acid is hydrochloric acid. This is done directly by neutralizing the acid or block the segregation of acid by gastric cells to reduce the acidity. So there are two ways of treating that. I'm talking about the first way, so direct attack on the acid. The second one is Rantac and Zantac. So those are all organic drugs. So these are the commonly used inorganic antacids: aluminum hydroxide, calcium carbonates, magnesium hydroxide, sodium bicarbonate, calcium citrate, and calcium tartrate. So these are the active pharmaceutical ingredients in most of the antacids that we have. And in addition, inorganic materials are also used as excipients. So excipients are the components of a finished drug product other than the API. So most of the tablets that you take may have a very small amount of the active pharmaceutical ingredient, but then they add a lot of other stuff, which is mostly inorganic, to improve the homogeneous distribution of the drugs or to improve the shelf life of the drug. Okay, so the additives help stabilize the drug dispersion as well as increase of the lifetime. This is what the pharmaceutical industry wants. They don't want a drug on the shelf to expire after 6 months. They want to extend the life of the drug to about 2, 3, 4 years, if possible. And that is done by adding inorganic excipients. Now, if you look at the excipients, most of the excipients are, again, something like aluminum acetate in the creams, aluminum hydroxide in the oral, aluminum silicate up to 81 milligrams. I don't like the word trisodium citrate, but basically you should call that sodium citrate, because citrate is, tri-negative anion, so there should be 3 sodiums in the formula, but that is the generic name the pharmaceutical industry uses, trisodium citrate. Similarly, calcium chloride and calcium carbonate, sodium carbonate, these are all used as excipients. So this is where the formulation of the drugs comes into the picture. There are lots of companies that work on improving the shelf life and the circulation time for the drugs by adding this FDA approved list. I mean, this is not the exact complete list. The complete list of compounds is about 50 to 60 of them. If you go to the FBI site, no, I'm sorry, FDA site, you will be able to see the complete list of FDA approved inorganic excipients. All right. So chief lead or arsenic or antimony or nickel poisoning. So what they use is 2,3-dimercaptone-1-propanol. Now, what is happening here is here the drug is a ligand, and this ligand selectively binds to one of these toxic metals and eliminates it from the bloodstream. So that is the whole idea. So dimethylcysteine is used to reduce the copper or the mercury contents. If you have lead poisoning, EDTA, ethylene diamine tetraestic acid, is a great chelating agent. So it kind of effectively binds with the lead and gets it out. And desferoxamine is to control the excess iron. Some people have not iron deficiency, but iron excess or aluminum excess. Even iron excess is also deadly, as deadly as iron deficiency. So you need to have just the optimal concentration of iron. If it is more or less, it's going to affect the human functionality. So these are all the drugs that are designed to control the concentration of most essential elements in the human body. So if you now look at the periodic classification, group 1, group 2, group 3, so on and so forth, the group 1 metals, such as lithium, sodium, potassium, rubidium, and cesium, these are all used for different purposes. For example, sodium and potassium help stabilize cell membranes and enzymes by electrostatic effects and osmosis, so that you can control. And crown ethers form stable complexes with alkali metals, such as sodium or potassium, and can be used to create imbalance of natural metals in the cells. Lithium ion used extensively in treating manic depressive disorders. If those of you remember in the beginning of the class, we talked about 7-Up, right? The drink that people added lithium. So that is the purpose of lithium. Even today, lithium is one of the first choices for the physicians to treat manic depressive disorders, such as suicide thoughts and the imbalance of the mental stability. The alkaline earth metals, which are basically the second group containing, the magnesium, calcium, strontium, and barium. As you all know, calcium plays an important physiological role in several processes, such as skeleton stabilization, cell division, blood coagulation, muscle contraction, and immune responses. So calcium supplements are widely used to improve the bone health. And barium sulfate is used as a contrast agent in the X-ray imaging for diagnostic purposes. So calcium and barium in that group are very important. Similarly, if you go to transition metals, those are the 30 elements, scanning from scandium to zinc and 3 periods down. Iron plays a very important role in the oxygen transport, and novel drugs such as ethylene diamine, bis, propylbenzylamino, iron 3 are used to fight the chloroquine-resistant malaria. This was a major discovery. Before this drug, for every 30 seconds, a child used to die in Africa. And that particular strain of malaria was chloroquine resistant. So we cannot cure that malaria by chloroquine. So now this complex came as a godsend. And now we are able to save a lot of humanity in that continent because of the presence of, this is again, inorganic complex drug. And cobalt isotopes are used routinely to test breast cancer through radioactive imaging. So this is again routinely used in the diagnostics. And copper iron complement each other in the electron transfer reactions in bioinorganic chemistry. This is a very important combination. Copper is found in the brain, heart, and liver. And copper deficiency can lead to brain diseases and anemia. All right, so this is very important. When you find somebody having anemia, it just may not be just the iron alone because of the importance of copper. So people suddenly look for the copper deficiency to see if that is the cause. And the antioxidant enzyme superoxide dismutase contains copper and zinc. This is administered as an anti-inflammatory drug. So as you can see, transition metals are also used in the anti-inflammatory things. And gold-1 complexes, especially the triethylphosphine gold-1 tetraacetylthioglucose, is used for treating rheumatoid arthritis. This is a FDA-approved drug that where the active pharmaceutical activity comes from gold-1 complexes. And silver has known antifungal and antibacterial activity. In other words, it's antimicrobial activity. So silver is a very important element that was known to humans for a long time ago. And the beginning of the inorganic chemistry class, we talked about the royal families where the kids are born with a silver spoon in their mouth. And part of the reason why silver spoon was kept in the infant's mouth is to attack any gum bacteria in the mouth. Of all the transition metals, zinc plays a very important role in several biological processes. Almost there are 200 proteins are known to contain zinc 2+, and without zinc 2+, those proteins will not be stable. For example, insulin becomes unstable, which insulin is not a protein, it's a peptide, but still without zinc, it is not stable. And carbonic anhydrase, a zinc-containing enzyme, is shown to catalyze carbon dioxide to HCO3-, and it's of importance in the respiration process. So people having respiratory problems are given zinc supplements because of the ability of zinc to catalyze CO2 to HCO3-. So these are all variety of applications of the transition metals. Now, if you come to the main group metals like bismuth and antimony, leishmaniasis, which is a disease caused by sandfly bites, affects millions of people, and sodium stibogluconate. Stibo is basically a name for antimony. So that is the only drug that is available for this disease. And bismuth complexes, as you know, are routinely used to treat gastrointestinal disorders. So Pepto-Bismol is a standard example. And bismuth subsalicate is used for the prevention treatment of peptic ulcers and diarrhea. So these are all known pharmacological activities of the transition metals in the periodic table. So if you now look at the summary, inorganic drugs play a very important role in biology and an increasingly important role in modern drug development and discovery too. There is a very intimate synergy between the function of the inorganic elements and the organic compounds of the human body for the reasons we talked about, the Lewis acid, Lewis base activity. And inorganic medicinal chemistry has a brilliant future and exciting opportunities are waiting. So there's a lot of work that is going on to design, to develop, and to test and market inorganic compounds as potential alternatives to the organic drugs. So that kind of gives you an idea about how inorganic chemistry plays an important role in the pharmaceutical industry. I'll now open the floor for discussion.
Hi, I'm curious if you know about anything about the bioavailability of metal complexes.
Bioavailability, I mean how soluble these complexes are in the thing?
Yeah, what percentage of the drug is absorbed by the body versus just going to waste?
Okay, part of the problem is not much of it is absorbed. So if you look at the chemotherapeutic agent, right, the cisplatin, you really put a little bit more platinum drug than what is required because the bioavailability is very small. But the biggest problem with these drugs, inorganic drugs, is once the activity is done, this platinum or the heavy metals, right, these things tend to segregate in the kidney areas. So getting them out of the human circulation is a big problem. So that's one of the reasons why there is a lot of cytotoxicity associated with these drugs. So people are now working on making them in the nanoscale so that you can reduce the dosage and increase the efficiency. That makes sense to you?
Yeah, thanks.
Great question. Bioavailability is a very important thing. Other questions?
Will you be posting these slides to Canvas?
They have already been posted, I think. Can you check to make sure that it is the case? I think I uploaded a PDF file, I believe. Is that right?
Yeah, they're there.
They're there. So all these slides that we have just, and I think Gurveer, you have recorded the conversation, right?
Yes, I'll put it on there.
So that should be available either today or tomorrow. So basically, you should know from exam point of view which element is good for what type of disease. So, for example, if it is you know TB, what elements are used for tuberculosis? I mean, we talked about antimony, right? Not sodium, not barium, not cobalt, not platinum. For anti-cancer activity, you know that there are platinum and ruthenium complexes that are being used. So you should be able to identify the disease and the inorganic element and be able to match it. Does that make sense? Like, for example, gastric disorders. What element is being used? Is it sodium, lithium, potassium, copper, silver, bismuth? For gastric disorders, which element is the one? Anyone wants to try?
You said bismuth, right?
You're absolutely correct, sir. So sometimes the question may be on what is the role of a excipient? What does it do? Does it improve the efficiency of the drug?
No.
No. What does it do?
Increase the shelf life of drug.
And then?
It also stabilizes distribution.
Correct, Carol. That's very important. Biodistribution is very important. And can I use any excipient? Or does it have to be FDA approved?
Have to be FDA approved. I think so. No, I don't. Probably.
It has to be approved by the FDA. And a lot of money is there in terms of Tylenol, for example, right? The adult Tylenol is different dosage compared to the children's Tylenol. And children's Tylenol comes mostly in the form of a liquid, correct? And that took a long time for the Johnson & Johnson people to formulate a drug using the paracetamol in children's formulation. So very low dosage, and kids are extremely picky, right, in terms of taking any drugs. So you have to really make it palatable for the kids. So you got to make it a little sweet and nice color, all that stuff. This is all done by excipients. So for breast cancer radioactive imaging, which element is used? Nickel, copper, cobalt, iron, manganese. We talked about this, right? Just a few minutes ago. Anyone remembers what element? No? Can you hear me?
Can you repeat the question?
What element is used in the radioactive labeling and cure of breast cancer?
Is it cobalt or isotopes?
It's cobalt, you're correct. It's the cobalt that is used extensively. We talked about the radioactivity nuclear transformations right in the beginning. So if you are creating, radiation therapy for the cancer, radiation therapy is purely administered from inorganic elements. That's another nuclear medicine has a lot to do with inorganic chemistry. The alpha emission, the beta emission, the gamma emission, all that stuff, we talked about that, right? Electron capture, positron emission, positron captures. I mean, we did a lot of nuclear transformations. They're all used extensively in pharmaceutical industry. Radiation therapy, for example. For the implants, which metals are used for implants, folks? Iron. Yes or no?
Titanium?
Titanium or tantalum, right? These are the only two that are used. I mean, there is so much there. I mean, we can't cover the entire thing. For example, if you look at dental implants, right? They use extremely strong negative thermal expansion materials. Have you heard of those materials, NTEs? When you replace the natural teeth with an artificial one, you don't want that material to expand when you drink coffee and contract when you have ice cream. That gives you excruciating pain. So you want to have a material that does not expand or contract when the temperature changes. You know, most materials, when you heat it, they expand. When you cool it, they contract, right? Neither are good for implants. So we have now a new technology where what they do is they take PTE materials, which is a positive thermal expansion material, which is a zirconium pyrophosphate, and they combine that with a negative thermal expansion material, the material that contracts when you heat, combine them and make the dental implants. That's why dental implants are so damn expensive. And if you don't get the right one, then you're going to have pain all your life. So my advice to you is don't go to that stage. Keep, good, take good care of take good oral care and keep your teeth all your life. Any replacement is going to be painful because of the expansion properties of materials. Similarly, the dental fillings are done by either aluminum fillings or sometimes they have silver metallic fillings. And sometimes people also use gold or silver as a teeth replacement. So if you look at the dentistry, there's a lot of inorganic chemistry in the dental field too. If you really think about this, this gives you a purpose of why we are learning inorganic chemistry. I may have given you a broad overview of how these elements are used in a lot of medicinal applications. So for those of your biochem majors, if you want to justify why you took inorganic chemistry, you can tell them this is the reason why. Other questions? Some people have been asking me about the composition of the exam. I have not written that, but there will be some questions on the lectures that we're going to do today and next Monday on the hydrogen. And, maybe there will be about 25 to 30 questions in total for the final exam, all multiple choice. So there will be some questions from the chapters that we have covered for the exams 1 and 2. Okay, maybe around 60 to 70% of the questions will come from those. 30% of the questions might come from the acid-base chemistry. Remember, I uploaded a presentation. Have you looked at that?
Yeah, I actually had a question from that.
Please, Samantha. Yes.
So in the video, you say that BF3 is a hard acid, but BH3 is a soft acid. Why? Why are they different?
It all depends on the. It's a little bit complex one. If I have to give you this, it's not the size here. It is the electronegativity difference between the boron and fluorine that makes it hard and soft. So if you look at boron and fluorine, right, the electronegativity difference is very huge compared to boron and hydrogen. So the way you can polarize the material, soft or hard, depends on how easily the electron cloud can be polarized, right? Some of that does it make sense to you?
Yeah, that makes sense.
Okay. So go back and again reread from that point of view. In fact, the BF3s, and I did not go into the lot of details, BCl3s, when you look at the Lewis acidity and the acid dissociation constants, they don't fall into the general idea about, like fluorine, is more electronegative, so it should be having a different property. But you cannot explain sometimes the acid-base properties by simple electronegativity argument alone. There are factors other than electronegativity coming to the picture. But most of the time, you need to know that if you have soft acid, you would rather have a soft base. Or if you have a hard acid, you have a hard base. That is when the formation constant, which is the equilibrium constant for the formation of the salt, is high. Was it helpful for you, that talk on acid-base chemistry? How to find the Ka1, Ka2 values and polyprotic acids, stability of the species, and the superacids we talked about? That'll be very useful for you in future. If you want to really find a strong acid to dissolve something, like wax, without oxidizing it, just dissolve it. You can think about the concepts that we talked about, the Lewis acids and the Bronsted acids. And even in the Bronsted acids, by modifying the composition, you can play with the acidity of it. Like sulfuric acid can be made more acidic by replacing one of the oxygens with fluorine. We talked about that in the class too. So these are all the things that you can learn from that chapter. All right. So we have now acid-base chemistry, we have medicinal inorganic chemistry, and then we have the hydrogen. So these are all the three topics that we discussed after the exam too. I'll make the exam final very easy, so you will not, as long as you have done exam 1 and 2 properly. And the other ones are descriptive questions, right? There's nothing much, no math here. There's no mathematics in solving problems in medicinal and organic chemistry. Just know the material and understand how the periodic table helps in the design of new drugs. So mostly conceptual, descriptive. All right, folks, if everything is okay, then I want you to read the hydrogen presentation for next Monday. We'll do it very quickly. A lot of slides there, but I will not be spending a lot of time on that. I'll just briefly go over some of the concepts, and I'll take any questions you may have on those presentations. So please read and let me know any questions you may have. And following Wednesday, next week, we will have a review session to answer any questions from chapters, all the chapters we talked about, the atomic structure, the molecular structures, the symmetries, the point groups, coordination complexes, the isomerism, all that stuff, from acid-base chemistry to medicinal chemistry to hydrogen. Okay, we will review that by Wednesday, and we'll take the exam Monday morning, 8 to 10 p.m. Okay, go. Any questions? Okay, if there are no further questions, thank you again for joining the class here. We will see you about the same time next Monday.
Thank you.
Thank you very much.
Have a good one.
You too.
Have a good one.
You too.